In this video, we're going to finish talking about how to graph all the rest of the trigonometric functions. So in the previous section, we talked about how to graph sine and cosine. Now we're going to talk about how to graph tangent, cotangent, secant, and cosecant. So we're going to start with tangent. The way we write the tangent function is we say y is equal to tan of x. So that's our most basic tangent function. And of course, in a second, we're going to talk about how to transform this, just like we did with sine and cosine. So the period of tangent is pi. So that's a little bit different than sine and cosine. Remember, sine and cosine had period 2 pi, but tangent and cotangent are both going to have pi. The range of tangent is negative infinity to infinity, so we can achieve any value, but we have a restriction on the stuff we can plug in. So I'm going to graph the picture first, and then we're going to go back and talk about the domain, because I think that's a little bit easier. So the deal with tangent is, since we have restrictions on the domain, we're going to have some vertical asymptotes show up in our graph. So our picture is going to look like this. I'm going to label the x-axis with pi over 2 and 3 pi over 2, and then negative pi over 2, and negative 3 pi over 2. And all of these tick marks are going to be vertical asymptotes. So to denote a vertical asymptote, I'm just going to draw a dotted line through each of these tick marks. A vertical dotted line, I should say. So this is how we set up our graph. And then the tangent graph, we're going to have basically a branch of tangent between each pair of asymptotes. So we're going to draw a point at 0, 0, and we're going to draw little branches coming off of the point as a smooth curve approaching the asymptote on each side. So each one of these is going to look like this, and so the other ones will be right in the middle of each pair of asymptotes, and we're going to do the same exact thing. So a few periods of tangent will look like this. Okay, so let's talk about how to write the domain. So the only numbers that we cannot plug in as x values are these multiples of pi over 2. So the way that we write this is we say that x cannot equal pi over 2 plus pi k, where k is an integer. So let's think about what this means. So we're starting at pi over 2, so you can imagine this is like this first asymptote here, and then we're going to add multiples of pi to it to achieve all the other asymptotes. So like if we were to look at the distance between these two asymptotes, this would have a distance of pi. So our formula makes sense. And then when I write this funny little symbol at the end, this k with the funny e and the z, this means k is an integer. So you'll notice that we use this little notation quite a bit in trigonometry. So I think it's important that you know what it means. Okay, so if that's the domain, then the vertical asymptotes must look very similar to this, except this time we're going to say that x actually does equal these values. So the vertical asymptotes will be x equals pi over 2 plus pi k, where k is an integer. Okay, and basically the reason we write this as a formula instead of a big list is because we have an infinite number of asymptotes, and so it's much nicer to represent this as a formula rather than trying to list out an infinite number of lines. So that's the tangent function. Now let's talk about cotangent. So cotangent we write as y is equal to cotangent of x. And just like tangent, it has a period of pi. The domain's a little different. We'll get to that in a second. The range is still all real numbers. And we'll talk about the vertical asymptotes in a second as well. So let's go ahead and draw the picture. So the way I'm going to label the x-axis for cotangent is I'm going to have some vertical asymptotes again, this time at pi, and I think that's the only one I'm going to draw here, and negative pi. And we also have one at 0. So to denote that, I'm just going to draw a dotted line on top of the y-axis. And then I'm also going to draw in my vertical asymptotes at pi and at negative pi. Okay, and then just like tangent, we're going to have a point in the middle of each of these pairs of asymptotes, except it's going to go the opposite way as tangent. So your branches are going to be drawn this way and this way instead of the other way like tangent. So we're just going to approach each pair of asymptotes like this. And so that's the graph of cotangent. So let's write in now what the domain is. So basically what we need to do is we need to get a formula for the vertical asymptotes, just like we did with tangent. So let's see. Well, we could think about it sort of the same way as tangent. So we could maybe start with this asymptote of 0. We could say x is not equal to 0 plus, and then the distance between two asymptotes is pi, so we could say 0 plus pi k. But that's just equal to pi k because adding 0 doesn't really do anything. So the way I'm going to write this is x is not equal to pi k, where k is an integer. Okay, and then the vertical asymptotes, again, would be just like the domain, except we're actually going to say that x does equal these values because we're talking about the lines themselves. So x equals pi k, where k is an integer. So that's the cotangent function. So let's talk a little bit about some stuff that we can do with this. So the period of tangent and cotangent is the distance between two consecutive asymptotes. So like in this cotangent picture, this area here would constitute one period of cotangent. And up here in our, let's see if I can move this up. Yeah. Up here in our tangent picture, this area here would constitute one period of tangent. Okay, so if I ask you in the problem to graph one period of either tangent or cotangent, we're just looking for one pair of asymptotes. Okay, another thing to note is that the amplitude of tangent or cotangent is undefined. So tangent and cotangent are not waves, so we can't really talk about the height of a wave if we don't have a wave to begin with. So that's why we don't have an amplitude. And then finally, to find the two consecutive asymptotes, to actually graph a period of tangent or cotangent, basically what we can do is set the inside of the tangent or cotangent function equal to the original asymptotes. So in the case of tangent, you would be setting the inside of the function equal to both negative pi over 2 and pi over 2. And for cotangent, you would set it equal to 0 and pi. So negative pi over 2 and pi over 2 were our initial asymptotes for tangent. 0 and pi were our initial asymptotes for cotangent. And we'll see an example of this in a second when we start to graph things. And then finally, transformations for tangent and cotangent follow all the same rules as sine and cosine. So we still have those four letters that we want to talk about, A, B, K, and D, and they do all of the same things that we talked about in 6.1. So let's jump right into some examples. So the first function we want to graph is y equals tangent of x over 2 minus pi. So the first thing we're going to do is analyze this equation before we actually get the picture. So maybe the first thing I want to do is find the vertical asymptotes. So what I'm going to do is I'm going to take the part in the parentheses and I'm going to set it equal to the initial asymptotes of tangent. So I'm going to say x over 2 minus pi is equal to negative pi over 2, and x over 2 minus pi is equal to positive pi over 2. So the first thing I can do is add pi to both sides. So we have x over 2 is equal to pi over 2, and this means x is equal to pi. And then in the second equation, I can say x over 2 is equal to 3 pi over 2. So x is equal to 3 pi. So these are going to be my two vertical asymptotes on my graph. So we have x is equal to pi, and x is equal to 3 pi. Okay, this SF that I have written at the top is what we call the stretching factor. So this is like the analog to the amplitude for sine and cosine. So the stretching factor will come from that letter A, which is that number that's multiplied by the function. However, in this case, we don't have one of those, so our stretching factor is just going to be 1. And next, I can find the period. So remember with sine and cosine, we took 2 pi and we divided by the number k. In this case, since the initial period of tangent was pi, we're going to take pi and divide it by k. So let's figure out what k is. So notice I could take 1/2 and factor it out of this inside. So we could say this is x minus 2 pi. Okay, so actually we notice that k is 1/2. So our period is going to be pi divided by 1/2, which is 2 pi. Okay, and so now I think, well, let's see, do we have any reflections? No, we do not have any reflections because we don't have a negative a and we don't have a negative k. So no reflection. Okay, so we'll talk about the x-intercept in a second, but right now we're going to graph one period. So the first thing we put on our graph are our x-axis labels. So we're going to have a label for each asymptote, and we're also going to have a label for that midpoint where we're going to have a point on the x-axis. So our 3 x-axis labels will be pi, 2 pi, and 3 pi. And then we want to draw in those vertical asymptotes. So we want to draw in a dotted line at pi and a dotted line at 3 pi. Okay, and then we'll have a point at that midpoint of 2 pi, and we're just going to draw it to where we approach both asymptotes, and then that's our tangent graph. So notice everything that we put on the graph here. So we had x-axis labels. In this case, we didn't have y-axis labels, but you could have those. Like we'll see one in a second where we need those. So that's going to happen if you have a vertical shift. Okay, and we'll see that in a second. You also need to draw in your vertical asymptotes. And finally, we need to graph key points and draw a smooth curve. So just like with sine and cosine, it's a lot to think about when you first start graphing these things, but again, the more you practice, the more this should become routine. So this is just a little checklist of things that I would want to see if I were to ask you to graph these on a test. And so again, my advice is when you're working through your homework graphing questions will be multiple choice. However, before you select an answer, what I would do is actually graph these things by hand so you get some practice, and I will include some extra practice problems on Moodle with my handwritten solutions so you can see how to do that. So the last thing we're going to talk about with this example is just the x-intercept. So the x-intercept is just the point where the graph crosses the x-axis. So here, this would just be the point 2 pi, 0. Okay, in this next example, we have the function y is equal to -3 times tangent of 2x. So once again, we're going to analyze the curve first, and then we're going to draw a picture. So maybe first I find my vertical asymptotes again. So we can take the inside of the tangent function, which is 2x, and set it equal to -pi/2. We can also do 2x is equal to pi/2. So solving these for x, we get x is equal to -pi/4, and x is equal to pi/4. So these are our two vertical asymptotes. Okay, the stretching factor, once again, comes from the number multiplied by tangent, which in this case it would be 3. But notice that it was actually a negative. So even though we're going to take the stretching factor to be a positive number, we're going to make a note that we will reflect over the x axis. Okay, the period we find by taking pi and dividing by k, and in this case k is 2 because that's the number multiplied by x, so the period is pi over 2. And then we'll talk about the x-intercept once we draw the picture. So again, when we draw our picture, first thing we want to do is label the x-axis. So we're going to put a tick mark for each vertical asymptote. So we have negative pi over 4 and pi over 4, and then we're also going to have a tick mark in the middle of those two asymptotes. So then I can draw in my dotted lines. And we'll have a point in the middle, and since we're reflecting this time, the tangent graph is going to go the other way. So it's going to look like a cotangent, but it's really just a tangent. Okay, so that's our picture. And now we can talk about our x-intercept. So the point where the graph crosses the x-axis is the point 0, 0, which is the origin. And we have one final example involving cotangent. So this time we have y is equal to 2 times cotangent of x over 3 plus 1. So this time, let's find our vertical asymptotes. So we're going to have x over 3 is equal to 0, and x over 3 is equal to pi. So remember the initial asymptotes of cotangent are 0 and pi, so instead of setting it equal to negative pi over 2 and pi over 2, we're going to set it equal to 0 and pi. And solving these equations, we get x is equal to 0 and x is equal to 3 pi. So these are my vertical asymptotes. The stretching factor is going to be this 2 that's multiplied by the cotangent. The period we can get by taking pi and dividing by 1/3. So we can think about this x over 3 as 1/3 times x. And so if we do this division, this turns out to be 3 pi. And then I want to make one other little note. We're going to have no reflections, and we're going to shift up 1. So we're going to shift up 1 because of this 1 that's added to the function at the end. Okay, and for this one, we're going to skip the x-intercept because it gets a little bit complicated, and I don't want to go there at this time. So let's draw some axes. We have our x-axis and our y-axis. So for this one, we're going to need to label the y-axis as well. So first I'm going to do my x-axis labels. So I have a vertical asymptote at 0. So to denote that, I'm just going to put some little hashes on the y-axis. And then I'm going to draw a second asymptote at 3 pi. And then I'm going to have a point at that midpoint, which is 3 pi over 2. Okay, and then to denote the vertical shift, I'm going to draw a tick mark on the y-axis at 1, and I'm going to put another dotted line going horizontally. Okay, so this is the setup for my graph, and now what I can do is draw a point on this new x-axis, this dotted line at 1, that's even with that midpoint of 3 pi over 2. So it's like an x-intercept, but I don't want to call it an x-intercept because we're not actually on the x-axis anymore, but it's still playing that same sort of role. So we've got this point here, and then cotangent, since we don't have a reflection, we're going to approach our pair of asymptotes going this way. And so that is our graph. So that is how to graph tangent and cotangent. The next thing we're going to talk about is how to graph cosecant and secant. So first we're going to talk about cosecant, and the way we write this equation is y is equal to cosecant of x. But once again, we can apply any transformation that we want. So the period of cosecant, you might guess, is 2 pi. So remember that secant and cosecant are related to sine and cosine. So these are going to have much the same information as sine and cosine. We'll talk about the domain after we draw the picture, and the range for that matter. Yeah. Okay, we can do the symmetry really quick though. So we know that cosecant is an odd function, and the way you can remember this is because it's like sine of x. Okay, so that's about all we can do right now. So let's draw the picture and then we can talk about the domain, range, and asymptotes. So anytime you graph cosecant, the first thing you actually want to do is graph sine. So we're going to start with a sine graph. So if you remember how to do that, we have our tick marks on the x-axis at pi over 2, pi, 3 pi over 2, and 2 pi. And then I'm going to draw in a second period in the negative direction just so you can get an idea of the repetition. And then we had an amplitude of 1, so we have tick marks on the y-axis at 1 and -1. And then we graph it as follows. So we start in the middle, we go up to the top, back down to the middle, down to the bottom, back up to the middle, and then I can do the same thing in the negative direction, just continuing the shape. And so I'm going to draw in this sine curve as a dotted line, because it's not actually going to be part of our graph, but it's going to help us to get the shape of our graph. Okay, so once I have my sine curve, everywhere that this sine curve touches the x-axis, we're going to draw a vertical asymptote through that point. So we're going to have a vertical asymptote at -2 pi, at -pi, at 0, so I'm just going to leave that as the y-axis, at +pi, and at +2 pi. So I know this looks pretty complicated, it's a lot of setup, but now that we've done all of this setup, the way that we actually graph the cosecant function, so maybe I'll switch to red just so you can tell the difference. Everywhere that we have a maximum or a minimum point, we're basically going to draw a little parabola shape that approaches the pair of asymptotes. So our graph is going to look like this. So it's not actually a parabola, but it sort of looks like that shape. Okay, so this is what the graph of cosecant looks like. It's just the little red arches that you see at the top and the bottom. So one period of this is going to be this distance here. So we've got between pairs of alternating asymptotes. And maybe I will highlight that just so it's a little more clear. So this area in here constitutes one period of cosecant. So now let's talk about the domain, range, and vertical asymptotes. So the domain we can get by just excluding the values of the vertical asymptotes. So we need to get a formula for these, and if you notice, they occur at everywhere there's a multiple of pi. So the way that we write the domain is we just say that x cannot equal pi k, where k is an integer. Now the range is sort of like the range for sine, but it's been flipped inside out. So if we think about where this is going, we can have any negative number. So we're going to start at -infinity. But the biggest number we can have for these bottom curves is -1. So we're going to go up to -1 and close it off with a bracket. And then for the top curves, they start at 1 and they go up to infinity. So we're going to start with a bracket, write a 1, and go up to infinity. So you can think of the range for cosecant sort of like the range for sine, but it's been turned inside out. And then finally, we can write the vertical asymptotes very similarly to how we write the domain, except now we say that x actually equals pi k, where k is an integer. Okay, so that's the graph of cosecant. Now let's go through the graph of secant. So this is really similar to cosine. So we write the secant function as y equals secant of x. Once again, the period is 2 pi. We'll talk about the domain, range, and vertical asymptotes once we get the graph. This time, the secant function is going to be even because it's like cosine. I'm writing that backwards. Like cosine of x. So, because secant is the reciprocal of cosine, the first thing we're going to do is actually graph a cosine curve. So let's remind ourselves how we do this. So we have our tick marks at 2 pi, pi, and then those little in-between marks, just like with sine. And then we'll have negative 2 pi, negative pi, and then the two midpoints. Our amplitude of cosine is still 1, so we have tick marks at 1 and negative 1. And now, if you remember, I start at the top, go down to the middle, down to the bottom, back up to the middle, up to the top, and I'm just going to continue this in the negative direction. So if I connect this with a dotted line, since this isn't going to be my graph, our cosine curve looks something like this. And now, just like with the cosecant curve, anywhere that this cosine curve touches the x-axis, I'm going to draw a vertical asymptote. So I'm going to draw one here, one here, one here, and one here. And then finally, I can draw in my graph of secant. So I'm going to switch to red just so you can tell the difference. So just like with cosecant, everywhere we have a maximum or a minimum, we're going to draw one of those little arch shapes that approaches our asymptotes. So the graph of secant looks like this. Alrighty, and just like with cosecant, one period is going to be between alternating asymptotes. So that would be like this distance here, and I'm going to highlight it just so you can tell, so it's a little more clear. So this area right here is one period of secant. So now we can talk about our domain, range, and vertical asymptotes. So the domain will be again determined by the vertical asymptotes. This time, our first vertical asymptote is at pi over 2, and each asymptote is a distance of pi apart. So we're going to do pi over 2 plus pi k, where k is an integer, and we need to exclude these values, so we say x is not equal to that. Our range is going to be exactly the same as it was for cosecant. You can think about it like the cosine range turned inside out. So we'll have negative infinity to negative 1, union with 1 to infinity. And then finally, the vertical asymptotes are just the values that we excluded from the domain. So it'll be x is equal to pi over 2 plus pi k, where k is an integer. Okay, so that is the graph of secant. So we just want to make a little note. Again, the period for cosecant and secant is the distance between alternate vertical asymptotes. And then this little note here is just giving you an algebraic way to solve for the length of a period. However, I like to just think of it as the sine and cosine graph. That's how I always do it, but it is there for you if you would like to reference that, but that's not how I'm going to do it. The way that we're going to do it is we're just going to graph the auxiliary sine or cosine curve, and we're going to get all of our information from there. So as an example, let's try y equals secant of 2x. So the first thing we want to do is identify the reciprocal function. So all we do for that is we just say, well, what's the reciprocal of secant? It's cosine. So all we do is replace secant with cosine. So the first thing we're going to graph is y equals cosine of 2x. So if you remember from 6.1, the way we graph cosine is we first analyze the function and think about everything we need. So our amplitude for this function is going to be 1 because there's no number in front of cosine. So our y-axis labels will be 1 and negative 1 since we also don't have a vertical shift. Our x-axis labels, we don't have a horizontal shift, but we do need to figure out the new period since we have a 2 next to x. And the way that we do that is we start with 2 pi and we divide by 2. So our period is pi. So what we're going to do is start our tick marks at 0 and end them at pi, and then we need to find those ones in the middle. So we have pi over 2, pi over 4, and 3 pi over 4. And now I can draw in my cosine curve. So I'm going to start at the top at 0, go down to the middle, down to the bottom, back up to the middle, and up to the top. So my dotted in cosine curve should look like this. The next step is everywhere this cosine curve touches the x-axis, we're going to draw in vertical asymptotes. So I'm going to have a dotted line at pi over 4 and a dotted line at 3 pi over 4. And then I can draw in my secant curve. So maybe I'll switch to red just so you can tell the difference. So we're going to have a little arch here approaching this asymptote, and then an arch here between this pair of asymptotes, and then an arch here between this pair. So this is one period of secant of 2x. For our next example, we're going to get a little bit more complicated. So we have y is equal to 2 times cosecant of x plus pi over 4. So this time we have a horizontal shift going on, so this one's going to be a little more complicated. So first of all, we identify the reciprocal function. So we have y is equal to 2 times the sine of x plus pi over 4. And now we can start to analyze our function. So we do not have a vertical shift, but our amplitude is 2. So my y-axis labels are going to be 2 and negative 2. And then my x-axis labels I'm going to have to figure out because I have a horizontal shift. So my initial x-axis labels are going to be as follows. So remember, I draw my 5 blanks, and we don't have a k value, so I'm going to assume that my initial period is 2 pi. And so I'm going to go from 0 to 2 pi, and then write the in-between points. So we have pi over 2, pi, and 3 pi over 2. So to find my actual x-axis labels, what I'm going to do is subtract pi over 4. So I'm just going to make a little note of that, and then I'm going to draw my 5 new blanks. And from each of these initial points, I'm going to subtract pi over 4. So then our points become negative pi over 4, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And then I can now label my x-axis. So I'm going to put a tick mark at minus pi over 4, pi over 4, 3 pi over 4, 5 pi over 4, and after extending this a little bit, 7 pi over 4. Okay, so now that I've labeled my x and y axes, I can draw in my dotted sine curve. So I'm going to start at the midline at my first key point, go up to the top, back down to the middle, down to the bottom, and back up to the middle. So when I draw in my dotted curve, it should look something like this. Okay, so now that I have my sine curve, my next step is to draw in the vertical asymptotes, and these will occur everywhere that the sine curve touches the x-axis. So I'm going to draw those in. And then now finally I can graph my cosecant curve. So again, I'm going to switch colors for your ease of viewing. So we're going to have an arch everywhere that we have a maximum or a minimum on the sine curve. So our cosecant curve will look like these red arches that I've just drawn in. And we'll do one last example with secant and cosecant. So this one we have y is equal to 3 times the secant of x minus pi over 3. So once again, first thing I'm going to do, identify the reciprocal function. So we have y is equal to 3 times cosine of x minus pi over 3. So now that I've identified the reciprocal function, I can start to analyze it. So first of all, I do not have a vertical shift, and my a value is 3. So my y-axis labels are going to be 3 and -3. And now I can start to figure out my x-axis labels. So we do not have a k value, so my initial x-axis would be the same as the last example. So we'd have 5 blanks, starting at 0 and going to 2 pi. So then we fill in our other labels. But this time I want to add pi over 3 to each of these, because we're subtracting pi over 3 in the equation. So my 5 new blanks, I'm going to add pi over 3 to each of these 5 points. So we get pi over 3, 5 pi over 6, 4 pi over 3, 11 pi over 6, and 7 pi over 3. And now I can write in my labels. So I'm going to have a tick mark for pi over 3, 5 pi over 6, 4 pi over 3, 11 pi over 6, and 7 pi over 3. And my next step is to actually draw in the dotted cosine curve. So I'm going to start at my first key point at the top, go down to the middle, down to the bottom, back up to the middle, and up to the top, and then I'm going to draw this in with a dotted line. So my next step is to draw in the vertical asymptotes. So I can draw those as dotted lines everywhere that my cosine curve touches the x-axis. And then finally, now that I've done all of the setup, I can draw in the secant curve by drawing a little arch at the maximum there, another little arch at the minimum down here, and then one final one on the right side there. So that is the secant curve that we were looking for. Now the last thing we're going to talk about in 6.2 is sort of how we ended 6.1. So instead of graphing a function now, we're going to be given a graph and find an equation for the graph. So for this first one, I'm going to add in some little directions. So for this one, you're going to use the tangent function. And when you get to your homework, it will tell you directions like this. So when it gives you the picture, it's going to tell you which function to use, because if it didn't tell you, it might be a little more confusing. So anyway, for this first example, we're going to use the tangent function. So first of all, let's think about our general tangent equation. So we have y is equal to d plus a times tangent of k times x minus b. So just like in 6.1, when we did these problems, our job is to find those 4 letters, D, A, K, and B. So maybe let's start with, D. So first of all, we have no vertical shift in this picture. So D is just going to be 0. Another thing to notice is if we want to talk about A, so we're going to assume that there's no stretch. However, you might notice that the tangent is going in the wrong direction. So that tells us that A is going to be -1. And so just as a note, there's no stretch, but graph is reflected. Okay, third, we can talk about the K value. So once again, this is it might be kind of the trickier one to find because we actually have to solve an equation. So first of all, let's identify the length of one period. So if you remember for tangent, one period is the distance between 2 consecutive asymptotes. So this would be one period of this graph. And it has length 1 because we're going from the y-axis out to the line x equals 1. So for tangent, our period, though, is equal to pi divided by k. So if our period is 1, and we're setting that equal to pi over k, well that means that k is just pi. So we figured out a value for k. And finally, we need to figure out the value for b. So this one again can be kind of tricky. So this definitely has to be shifted a little bit because if you remember the original tangent graph, it was symmetrical about the y-axis. Or, no, I shouldn't say that. It's symmetrical about the origin, but it sort of splits over the y-axis. So like our initial tangent graph, and I'll do this in red so you can tell the difference, would have been here. So we would have had symmetry on the asymptotes, I guess I should say, and we probably would have had a branch going like this. So the question we need to ask ourselves is, how far did we take that red curve and shift it to make it the blue curve? So I think the easiest way to do this is just to look at the asymptotes and how far they've shifted. So our initial asymptote would have been at negative 0.5, but it shifted up to 0. So we had a shift to the right by 0.5. So this tells us that b is going to equal negative, or no, sorry, b will equal positive 0.5. Okay, so that one is definitely tricky. So I think the best way to do this is just to draw all over the picture you're given. Draw what the unshifted curve should look like and figure out where did you have to shift it to reach the picture that you were given. So that's how we got this b is 0.5. So now all we have to do is plug all of these numbers in to the general equation. So our equation will be y is equal to negative tangent of pi times x minus 0.5. So this is the entire equation with all 4 letters plugged in. So that one was kind of tricky. Hopefully this next one will be a little bit nicer. So for this next example, we're going to use the cosecant function. So let's just start by writing out our general cosecant function. So we have y is equal to d plus a times cosecant of k times x minus b. Okay, so once again, we need to find d, a, k, and b. So first of all, let's find d. So there's no vertical shift, so d is equal to 0. Second, we notice from the graph that each of these little arches is even with 2 and negative 2. So the minimums of the top arches is even with the line at 2. So if we sort of draw that in, you can see that. And the maximums of these bottom arches is even with that line negative 2. So what we can infer from this is that a must be 2. And as a note, I'm going to say this is because the amplitude of the sine curve is 2 with no reflection. So it might help you to actually draw in a sine curve here. So we can do this by just connecting all of these dots. And you'll notice that the curve looks like a proper sine curve. It's going in the correct direction. It hasn't been shifted anywhere. And it hasn't been reflected. So our a is going to be positive 2. So third, we can find k. And again, the way we do this is we figure out first how long the period is. So one period on cosecant goes between alternating asymptotes. So this would be one period here. And we can see that it has length 2 pi. So we can say the period is equal to 2 pi divided by k. But our period is just 2 pi. So k must be 1. And then finally, we can talk about the phase shift. So we need to find our value for B, but as you can see from the sine curve that I sort of sketched in there, we haven't shifted the sine curve anywhere. So it's starting at 0, it's going up, middle, down, back to the middle. So it's just a normal sine curve with no phase shift. So since there's no phase shift, we know that B is just going to be 0. So I think this example is a little bit simpler than the first one, but sometimes that gets confusing, right? Because you've got all these zeros and ones floating around. And so even though it makes your equation easier, it's actually a lot less to look for. So let's put this all together and get our full equation. So if we plug in all the numbers that we got, we should just get that y is equal to 2 times cosecant of x. So the reason this looks so simple is because we didn't have a vertical shift. We didn't have any kind of stretching or shrinking because the k value was just 1, and we also did not have a phase shift. So the only thing we actually had to plug in was that value for A. So this concludes our lesson for 6.2.